Okay, so we want to find a set of parametric equations for the line of intersection of the two planes, given by x minus y plus z equals 1 and 2x plus y plus z equals 0. Okay, if you think about it, I'll try and draw this. I can't guarantee it'll be a work of art. So if one plane looks like this, as long as the planes aren't parallel, then they should intersect each other in a line, shouldn't they? So let's say the other plane kind of goes up at a steeper angle like this. Comes down here maybe. Then hopefully it's clear that the way they're going to intersect is in a line. Does that make sense? Visually, does it make sense to you? If you can interpret my 2D drawing that's supposed to look like 3D. So how do you find the parametric equations of that line? Okay, think about it. The points x, y, z that make up this line of intersection satisfy both equations of the line, or of the planes, of the two planes, right? They have to be solutions to both equations of both planes. Does that make sense? So x, y, z, if they're on the line, they are solutions to both planar equations. So finding the parametric equations of the line breaks down to solving the system of equations represented by the two planes. So all you have to do is, okay, I'm going to write them down. X minus y plus z equals 1. And 2x plus y plus z equals 0. Think of this as a system of two equations, three unknowns. Two equations, three unknowns. If we can solve, it's a dependent system, so when I say solve it, the best you can do is write each coordinate in terms of one of the other coordinates. So you could write every coordinate in terms of x, or every coordinate in terms of y, or every coordinate in terms of z. But anyway, you solve the system, the points you get that solve that system have to lie on that line of intersection because they satisfy both planes. So here's the idea, you guys. We could think of the elimination method. If we just add the equations together, which unknown goes away? 1. So we're going to solve this system. And we're going to solve using elimination. So we add them up. We get, what do we get? 3x plus 2z equals 1. Now, obviously, we can't get a single number here, right? But we don't want a single number because the line has an infinite number of points associated with it. So we want a set of parametric equations in one variable. So what I could do at this point is I could solve for z in terms of x, I suppose. I'll put everything in terms of x. So, but this is negotiable, by the way. You could solve for x in terms of z. It wouldn't matter. Well, okay, yeah, actually, if I do what I said I was going to do, I'd have to solve for z in terms of x, so I could replace z with something in terms of x. So I'll do it that way. So I'll get z, if I do that, I'll get z is equal to 1 minus 3x. So subtract 3x from both sides and then divide by 2. Does everybody see what I did there? Okay. So I also need to get y in terms of x. So the idea is my parameter is going to be x. And so I need to get each variable, x is equal to x, that's easy, but I need to get y in terms of x, and I have z in terms of x. Once I have each variable in terms of x, then that is my set of parametric equations. It's got to be because it's the solution to the system. And the solutions to the system, by definition, satisfy both equations. So they've got to lie on the line. Okay, so how do I get y in terms of x? Well, it's the substitution method, so you could just take one of the equations. Well, I'm sorry, originally it was the elimination method, but then once you do the elimination method, you plug back in to get the other solution. Remember that? So if we plug in z in terms of x back into one of the equations, we can solve for y in terms of x. So, okay, if we do that, we get x minus y plus z, but that's 1 minus 3x over 2 equals 1. All right, let's clear up that denominator of 2. What could I multiply through by? 2. So I get 2x, help me out here, plus the numerator equals 2. Good. All right, so combine like terms, 2x minus 3x, negative x, minus 2y, plus 1 equals 2. Does everybody buy that? Okay, remember what I want. I want y in terms of x. So that means I'm going to leave negative 2y on the left side and move the minus x to the other side by adding it to both sides. Move the plus 1 to the other side by subtracting 1 from both sides. What do I end up with if I do that? So I get negative 2y equals x plus 1, or 1 plus x. And then solve for y by dividing by negative 2, and I get x plus 1 over negative 2, same as negative x minus 1 over just 2. So I moved the negative up top and distributed it. Okay? All right, so I know this looks weird, but I'll put it together for you. So as solutions to the system of equations, you can write out x is x, right? Y in terms of x is this guy, so your second coordinate becomes this guy. Z in terms of x was what? This guy. Okay, so your parametric equations are just this. X equals x. Now you could change this x to a t if you want. If you don't like having x equal to x, you could change it to a t. You could just say let x equal t. Doesn't matter. And then that changes all of these to t's as well. But for right now, let me just make a point. You have x equals x, y equals negative x minus 1 over 2, and z equals 1 minus 3x over 2. These are your parametric equations. In other words, as an ordered triple, every single one of those coordinates must satisfy the equations, both equations of both planes. So they must lie, that set of points that I've circled must lie on the line of intersection. So those points must form that line, long story short. Now most people don't like using the x twice, so you could just say let x equal t, and then it looks more like what you're used to. You get x equal t, so another way to write your parametric equations, x equals t, y equals negative t minus 1 over 2, and z equals 1 minus 3t over 2. Okay, so that would be one representation of the line of intersection. Now, parametric equations are not unique. So if you had chosen to put all of the coordinates in terms of z, or all the coordinates in terms of y, you'd have a different set of parametric equations that represent the same line. And that's okay, because if you were to plot every point, which you couldn't possibly do, but if you could, it would still represent the same set of points overall.